Hello everybody, and welcome to another video on my channel. This will be the final video in my applications of derivatives series in my calculus series before we move on to integral calculus, which is the other half of calculus and involves integrals. So I think that's pretty much about all I have to say, and let's move on to the video. The prerequisites that we need is first, related rates. We need to know what that is. I covered that in a previous video. And we need to know what optimization is. I also covered that in a previous video. So what we're going to be doing is we're going to be combining these two by optimizing quantities that change over time. Now, when do we use both techniques? It's pretty simple. When a quantity needs to be maximized or minimized and the constants change with time, or we need the rate at which the optimal value changes. Basically, a few examples are like maximum area with changing perimeter and minimum distance problems with moving objects. Now, our general solution strategy is first, set up the optimization function, then express constraints in terms of time-dependent variables, find the optimal condition, then differentiate with respect to time. Number 4, substitute known rates of change. And number 5, solve for the required rate. This is our example problem statement, where we have a 10-foot ladder leans against a vertical wall. Now the bottom of this ladder slides away from the wall at a rate of 2 feet per second. Find the rate at which the angle theta between the ladder and the ground is changing when the area is maximized, given the ladder length, 10 feet, which is a constant, and the bottom sliding rate. What we're going to do is, instead of using calculus for the optimization, we're going to use some calculus, but also a little bit of geometry. And it all involves using squares. Now, a square is a rectangle with the highest ratio of an area to a perimeter, and let me prove that to you. Let's say we have one side of x and one side of y. What we have is the perimeter is going to be equal to 2x plus 2y. So p is equal to 2x plus 2y, and the area is equal to xy. This is what it is for a rectangle. Solving for y, let's say we have a fixed perimeter. In this case, over here, since all the sides are 2, it's going to be equal to 8. So 8 is equal to 2x plus 2y. Now, what we can do is we can solve for y in terms of x. So y is equal to 4 minus x, and since area is equal to xy, is going to equal to x multiplied by 4 minus x, or this is also equal to 4x minus x squared. So now that we have that, we can differentiate this to get 2x, or to get 4 minus 2x is equal to dA by dt, which we're going to set as equal to 0 for our optimization problems. So then what happens is x is going to be equal to 2, and then by y is equal to 4 minus x, y is also going to be equal to 2. And those two, since they're the same size, that's a square. But to prove that, let's take the second derivative. So 4 minus 2x, the derivative of that is negative 2, is the second derivative, is equal to d squared a divided by dx squared. And since it's negative, that represents a maximum. So a square is the maximum area within a given perimeter. So now that we have that, Now that we have that maximum area within that given perimeter, we can move on to the maximum area for a triangle. Now the maximum area for that triangle is going to be an equilateral triangle, and let me show you how. So since we know that the highest for quadrilateral or any rectangle is a square, what's gonna happen is that we can do a line y is equal to x, 0 is less than x is less than 2, and this, if we split this creates an equilateral triangle. On top of that, any rectangle we can split in two in order to get what we want. So let's say we can create a different rectangle. So we can copy this. We can create a different rectangle. So we can copy this, then this, then this, then this over here. And let's say we move this. So I'm going to move this to be 2.5. X is equal to, let's say, 3.5. Then y equals to 0 can be moved. But we can move the constraints from 2.5 to 3.5 and so on. Let me quickly finish moving everything. So we have a rectangle over here, and we can draw a line. Y is equal to 2x. And then we can drag this to the right. The 2x minus 5 gets us what we want. And then we can do 2.5 is less than x is less than 3.5. And now we split this rectangle into a right angle triangle. But I know the perimeter and everything is a bit different. But what this is this is showing that you can split any rectangle into two equal right angle triangles. But since the area of the square is the maximum for a given perimeter, that means it has to be an isosceles right triangle, not an equilateral triangle. I'm sorry if I said that earlier. It has to be an isosceles right triangle where these two sides are equal. So these two sides would be equal to the sides of the ideal square. So since we have that, the next thing that we can do is figure out what those sides exactly are. Now an isosceles right triangles, the sides for an isosceles right triangle have the ratio of 1 to 1 to square root of 2, where square root of 2 is the hypotenuse. So what we can do is, since 10 foot is a hypotenuse, and that's hypotenuse of the triangle, and that's gonna be divided by the square root of 2, we'll get 10 divided by the square root of 2 is as the optimal side length of the triangle, but this is going to be equal to 5 multiplied by the square root of 2 for both sides. Now, the next thing we're going to need to do is to find the angle theta where it is at this optimal area. So, what we can do is we can say the horizontal distance, or the tangent of distance really. So we have tangent of both sides, since they're the same, divide by each other. So 5 times the square root of 2 divided by 5 multiplied by the square root of 2. So then this is going to be equal to the arctangent. It needs to be arctangent of 1, and this becomes pi over 4 radians or 45 degrees. Either one will work. So this is the angle at that specific moment. Now the next thing that we can do is we can set up an equation. Basically, let's say we have x, or the length of that. So what we can do is we can have sine of theta can be equal to, now where we have the vertical distance, y divided by 10, which is the hypotenuse. So what we can do with that is we can differentiate this. So that's going to be cosine of theta at that moment multiplied by d theta divided by dt. Wait, sorry, no, it has to be x by 10 and cosine, never mind. So it has to be negative sine theta multiplied by d theta divided by dt with respect to time is equal to dx divided by dt, dx divided by dt multiplied by 1 by 10. So now that we have that, sine of pi by 4 at that instant would be square root of 2 by 2, but then dx by dt would be 2 divided by 10, so we have 1 over 5 is equal to negative the square root of 2 divided by 2 multiplied by d theta divided by dt. So this would give us d theta divided by dt is equal to negative 2 divided by 5 times the square root of 2, or we can say negative 2 multiplied by the square root of 2 divided by, now since we're multiplying by that, we get 5 times the square root of 2, so 10. And with that, we can also just get the square root of 2 divided by 5, and that's going to be about 0.2 something. So that's pretty much it. That's all it's going to be for this problem. That's about it, and there we have it. Our example for today will be solved. It's pretty simple, and I really enjoy the fact that we could use a geometric proof instead of just relying on pure calculus, because that would take a pretty long time. Let's look at the solution. We get the square root of 2 divided by 5, and we get about negative 0.283 radians per second. As I said, it was negative 0.2 something. So that's pretty much about it. And here are a few common mistakes to avoid. Number 1, forgetting to establish the optimization condition. Number 2, not clearly identifying what changes with time because some things are constant. Number 2, confusing the optimal value with the rate of change. So confusing the role of optimization with the rate of change. Number 4, incorrect chain rule applications. Number 5, missing constraint relationships. And number 6, not checking if the condition remains valid. Here are a few problem solving tips. So draw a clear diagram with all variables labeled if you can. Number 2, write relationships before differentiating. Number 3, check dimensions for consistency. Number 4, identify the optimization condition or verify that it's satisfied. And number 5, interpret the sign of your answer. Basically, here is the practice problem for today. Over here, the cylindrical water tank. And it's a pretty interesting problem in my opinion. So definitely try this, it'll really help you a lot, and the solution is over here also if you need to check. And thank you so much for being in these videos, watching until the end. It really helps a ton, and I'm so happy you're here. If you enjoyed this and found it educational, please make sure to like, subscribe, and hit that notification button for more awesome videos just like this. And thank you so much for watching. See you in the next one, and bye-bye.